another week. Yeah, so yesterday the education minister announced that we're at this until at least May 31st, so sneaky suspicion that this might be the way we learn for the rest of the year, but we will see. Okay, get us through chapter 5. We're well on our way, guys. We have 8 chapters, so if we can get through chapter 5 at the end of this week, then move on to trig. It's a whole new world for us. Okay, 5.4 is solving rational inequalities, which is actually just one extra step from the 5.2 lesson. So it's going to be very straightforward if you understood 5.2. There is one thing I need to add that for some reason I forgot in 5.2. But the idea was, remember, a rational expression is a polynomial divided by another polynomial. So we called the rational expression h of x, and it's really just f of x divided by g of x. Now, in order for us to graph rational functions, we set up a system of 3 steps. First, we looked at, are there any asymptotes? And we know how to find vertical asymptotes, horizontal asymptotes, oblique asymptotes. Okay, so there was 3 different things we found. Then I said from there you're going to find x and y intercepts. No problem. From there we do what's called the positive negative chart, where we find out where the function is in the positive part of the Cartesian plane and where it's in the negative part. What I neglected and I didn't realize was going to show up in the homework is that sort of at a stage before we still want to make sure the positive negative chart is your very last chart, very last step. So after intercepts, you have to see if there's any holes in the function. Okay, and what I mean by a hole is the idea of a place where the function does not exist. And we show that by doing, instead of a closed dot, an open dot. Okay, we've seen open dots before where we did like greater than or less than, where it didn't equal the spot, but it went up to that spot. It's a similar idea here. So the way we find if a hole exists is when you sub a specific x value into f of x and to g of x, if they both the numerator and the denominator become 0 because of that. So you're looking for an x value that makes both the numerator and denominator 0 at the same time. So basically you're looking for a situation where something would have canceled out, because if you put an x value in there, they both would become 0. So what we call the expression 0 divided by 0, that's called kind of an indefinite expression, and we say that the function doesn't exist there, so we draw a hole. So as an example, if you had this function, this is polynomial, right? You have a quadratic over a linear function. If I factor the quadratic, it's a complex trinomial, I realize it factors to 3x minus 5 and x minus 2. What this sets up, obviously we know that one of the restrictions is that x can't be 2. Okay, that whole idea of this is actually a vertical asymptote. But when we factor, we realize that if x equals 2, not only does the denominator become 0, but also this portion of the numerator. Well, 0 multiplied by anything is still 0. So if I sub in an x value of 2, then this function h of x becomes 0 divided by 0. That's what we don't want. So we say a hole exists at x equals 2. And if you graph this function, really what's left here, h of x, because these canceled, all you're left with is 3x minus 5. Well, that's just a line that has a y-intercept of negative 5 and a slope of 3. When you hit an x value of 2, you'll draw an open hole. So the line still goes right up to that spot, an open hole, and then continues through. So it still looks like a continuous line other than that one spot. So it's like this function exists everywhere except for when x equals 2. Okay, it's not allowed to equal 2 there. It's not enough that it's just a vertical asymptote. It happens to be a hole when it hits the function in both ways. Okay, so I neglected to say that in 5.2, so just amend your 5.2 homework if you haven't done it yet, to realize that not only do we have to find asymptotes and intercepts, but before we do the plus minus chart, we should also see if holes exist. Okay, now moving on with 5.4, I'm just going to do one example that's going to go over all of these crucial steps, and at the end talk about what happens if it's not an equation, if it's an inequality. Okay, that's going to become just an extra step to what we already did in 5.2. No more difficult, just one extra line. Okay, on the note on the internet, I've also taken up a question from, Mr. Todd did, in the past took up a question from the textbook as another example of what's going on. So take a look at that. But for inequalities, the only difference, what you really want to make sure you do is graph it. Once you graph it, it makes it very easy to see where it's greater than, less than, greater than or equal to, less than or equal to. Okay, so you want to graph it so you can see, is it greater than a specific value? Is it less than a specific value? So you want to make sure that you go through the steps to graph it. So the example that's in the note is to solve where 2x squared minus 3x minus 5 over this, oops, minus 3x, where this is greater than 0. Okay, so in 5.2 we would have said equal 0 and would have went along, or 5.3 we would have had equal 0 and went about our way. So in order for you to solve it, we still want to do it sort of in the same way. We want to set this up. Don't worry about this till the very end. I'm going to put a line here so that I remember. That's the whole point of the question. We want to find out when is this rational expression greater than 0. That's the main question. But in order to get that, we have to see, what does this look like? Well, in order to see what it looks like, we're going to just let f of x be this function, 2x squared and then, of course, if you can factor it, that should be your first step, because factoring it makes everything easier to see. So this one, trinomial, negative 5, 1, good, negative 5, positive 1, x and x, two numbers that multiply to negative 18, add to negative 3. Okay, so we get it set up like that. Now in this one you can see right away there are no holes, because there's no value of x. Nothing is set up as a cancellation here, right? So there's no specific value of x that makes this 0 over 0. So we know there are no holes. So that's the one we just looked at. If we did things in the order in which we want to inspect things, maybe I should write this somewhere. We want to do asymptotes first. So the idea is, and I did this in specific order last time, I did vertical, then horizontal, then oblique. Vertical asymptotes come from the denominator. You're basically saying, where does the denominator equal 0? And that's where your vertical asymptotes will occur. So we know enough to say, well, if this denominator equals 0, then one of these values equals 0. So either x equals 6 or x equals negative 3. And those there really become the first two things that you're going to need to graph. Now I'm going to come up here and sort of erase this part. I'm going to start my graph up here so I can see what it looks like. I don't want to erase the question. This is the problem. You don't have enough board space. We're now taking what used to be a classroom full of blackboards all the way around the whole classroom and putting it to one little tiny 1.5 by 3 foot board. Okay, so if I was to graph this, get a general idea of what it looks like. Again, if you had a graph paper would be helpful. Go across here. So I like to graph as I go so I make sure I don't forget something. So I do find vertical asymptotes at x equals 6, 1, 2, 3, 4, 5, 6, up and down, right through, and at x equals negative 3. Okay, so those ones I have put on check. The next thing I want to do is check horizontal asymptotes. Okay, and horizontal asymptotes, this is where we start comparing the degrees of the numerator and denominator. Remember, there was 3 rules. 1, if the degree on the top is less than the degree on the bottom, what happens? If the degree is greater than the degree on the bottom, what happens? And the last one, if they have the same degree, which is this scenario. They're both degree 2, right? This is 2x squared, this is x squared. This is same degree, and the rule with same degree was you take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator, and that becomes your horizontal asymptote. So our leading coefficient is 2, because it's in front of the x squared, and our leading coefficient in the denominator is 1. So this remember, it's a horizontal asymptote, so it's a y equals, is y equals 2. So I have to go up to y equals 2, and I now have a horizontal asymptote. And remember, these asymptotes, the graph has to approach them. So we're talking about a graph that's somewhere in this little section, kind of like a little quadrant, maybe up here, maybe over here, has to go all the way through. It can't go through, maybe down here like a little parabola shape. So you're kind of looking at, is it the boomerang shape over here or over here? Is it a parabola here? Is it a parabola here? Is it boomerang? Is it boomerang? It doesn't have to be the parabola. It can be sort of a W. But the idea is it has to approach this one, and it has to approach the red one, and it has to approach this one. So there's only so many shapes that can fit in that general area. But we're already starting to see a picture of what this is going to look like just based on these. Okay, the next one is, does it have oblique asymptotes? And oblique asymptotes happened when the degree of the numerator was exactly 1 more than the degree of the denominator. But because these have the same degree, we would say this does not exist. Okay? So there are no oblique asymptotes. So that takes care of our first scenario. How do we graph with asymptotes? Okay? Number 2 on our list of things to do was intercepts. Okay, so you have to look at 2 different things. You have to find an x-intercept, and you have to find a y-intercept. Okay, so both of those, this is grade 9 math. To find an x-intercept, you let y equal 0. Well, y is just f of x. Okay, so remember, if we're talking here, let's just put a y to make our life easier for a second. If y equals 0, and I need to solve for this, then when I multiply 0 by this denominator to clear the denominator, the whole thing becomes 0. So I'm really looking at the scenario 0 equals just the numerator. 2x minus 5, x plus 1. So this occurs, obviously, when do these 2 things, when multiplied together, equal 0? Either this one equals 0, in which case x equals 5 over 2, or this one equals 0, x equals negative 1. So these are x-intercepts of 5 over 2, 0, and negative 1, 0. So again, as soon as I find something, I want to graph it so I don't forget it. So 5 over 2 is 2.5. So 2.5 and 0, that's an x-intercept, and negative 1 and 0. That's an x-intercept. Okay? Helpful to us for sure. Then we go over to the other side and we want to find y-intercepts. Same idea, you let x equal 0. Well, when I let x equal 0 here, I get y equals, when I put a 0 here, 2 times 0 is 0, minus 5 is just negative 5. Put a 0 in here, I get a 1. 0 here, I get negative 6. 0 here, I get a 3. So I get a y value of negative 5 over negative 18. Obviously, negative divided by a negative is just a positive. So this is a y-intercept of 0 and 5 over 18. So 0 and 5 over 18 is less than a half. I don't know. It's an estimate. You're going to get a point right here. Okay, and again, our kind of 2B step that we want to look at. Are there any holes? Can't really see anything because of my rug here. So somewhere you're writing no holes, which we already talked about. Okay, there's no x value that makes this 0 divided by 0, so no holes exist. So the last step in our evaluation here has to be, running out of space, has to be the plus minus chart. And in order to set up the plus minus chart, you really want to look at where this function is going to be positive or negative, and the things that are important are the vertical asymptotes and the x-intercepts. So when we look, we have 2 vertical asymptotes, 2 x-intercepts, so we have 4 different things. That means we're going to have 5 ranges. I think this is kind of too small down here. I'm going to erase for a moment. I just want us to be aware that we want to find out where it's greater than 0. So I'm going to put this idea back over here. Where is it greater than 0? That's the question we're trying to answer. This will allow me to erase some of this. I want to erase this so I can put a good plus minus chart that everyone can see. Okay, so this is step 3, the plus minus chart. See above. Okay, so we have to look at all these. You start from the left. You're really looking at, first of all, when I set up my first column, I really want to look at my numerator, 2x minus 5, x plus 1. That's one thing that I'm going to do. And my denominator, x minus 6, x plus 3. If you want to do them all in one stage, you can. It's totally up to you. And then this is my whole function. And that's the part I'm really going to be interested in. Now in terms of what are the ranges I'm looking at, you start on the leftmost side. So we're saying anything less than this boundary, which is -3. What is it there? Then we go between the asymptote and the first x-intercept. So between -3 and -1. Then we go between -1 and the next intercept, which is 2.5. Oops. You can keep it 5/2 if you want, doesn't matter. 2.5. And then between 2.5 and 6. And then greater than 6. See why I wanted to move this to a bigger area. Okay? So then, as you go through it, you're really looking at the situation. When you pick a value in each of these intervals, substitute it in, and see what you get. So again, if I pick any value less than -3, say I pick -5, and I sub it into here. Well, if I put a -5 in here, I have a negative times a negative, that's a positive. Okay? Same thing here, positive. So overall, when I take a positive and I divide it by a positive, I get a positive. And this is the one I'm interested in the end. Okay, so you'll go through, pick a value between -3 and -1, something like -2. A positive, put a -2 in here. This time you get a negative. When you divide a negative by a positive by a negative, you get a negative. Okay, so you get the idea. You will put your own values in. I am assuming you can all substitute into these little basic quadratics. A value between 2.5 and 6, and you get a positive and then a negative. So to be a negative, and anything greater than 6, you get a positive and a positive, which works out to be a positive. Okay, so when you go to graph this, and I guess I'll graph it in blue, seeing as that's what I did my intercepts in. Anything less than -3, so on this side, you're concerned with what portion is it going to be in. It has to be positive. Okay, so when it's less than -3, it's going to be positive, which means it's going to stay up here somewhere. Okay, is it possible part of the graph was here? Well, maybe, except for because there's no intercept on the axis, it couldn't continue to approach this way, so you know it has to go above. Okay, anything between -3 and -1 is negative, so you're approaching down here on the negative. You then hit that, that's where it stops. Between -1 and 2.5 is positive, which you could probably have guessed. Okay, between, oh sorry, what did I do here? Between -3 and -1 is positive. Negative, positive. Oh, this whole thing, sorry. -1 to 2.5, that's all positive, sorry. I stopped at the y-intercept, I should have went all the way. And then between 2.5 and 6, it goes down. And then the last step, x is greater than 6, it has to be positive, so you're going to end up back up here. Okay, so this is all from 5.2. That's the exact same question. The question here says, when is this function greater than 0? So we're looking at this, and imagine that this marker is the x-axis. When is it greater than 0? Well, in this section it is, in this section it is, in this section it is, i.e. where it's positive in the chart. That's what it's asking you. This is greater than 0. Okay, so you're really looking at the answer is when x is less than -3, when it's between -1 and 2.5, and when it's greater than 6. So you would say all of these, f of x is greater than 0 when x is less than -3, it's between -1 and 2.5, and greater than 6. Okay, if you want to look at the next solution, there's one fully done in the note for you where you look at another inequality that has a greater than or less than or equal to 0, and then that will help you sort of figure out that other type of situation. Okay, that will take care of chapter 5 for us. Okay, inequalities seems like a big kind of concept, some of this stuff, but again, follow the steps: asymptotes, intercepts, holes now that I forgot, and the plus minus chart, and you're good to go. Okay, it's not, the more questions you do, the better you're going to get at it. The assignment that comes out on Thursday will be very similar to the other assignments. It's not as long as a test. Obviously, you can use your own work as your support. So that's it for this week. You'll just work on the practice test. When you see a rate of change question, just don't do it because we've taken that out of the curriculum. Maureen, you want to come say hi? Yes? You want to come show them? Okay, come on. Morgan, say goodbye. Something very exciting happened to Morgan yesterday. What did you do?
I lost my tooth.
She lost her first tooth. Show us. That one right there. First tooth gone. Tooth fairy came. $10. Hard times. Quarantine. What do you got there? Putty? Mm-hmm. Okay. Go turn the camera off.
Okay.
You want me to?
I want to.
Okay, you find the red button and you press stop. You see it on the side there?
Yeah.
Okay, press stop. Did you stop it?